Well met 216ers and good evening. What follows is a video that surveys what you're up against on Project 1. The goals for the video are to help orient you towards how to go about starting the project and make some initial steps on it, as well as give a brief overview of what the topic for the project is like. We'll start with the latter part of that and say that the objective here is to solve some little two-dimensional mazes, the kinds of ones that perhaps you still do for fun, but likely did as a kid at some point. This is often done with computer algorithms, notably depth first search and breadth first search. One of the advantages of our choice of breadth first search is that it will lead to shorter paths than what the alternative depth first search might have, but both of those are worthy algorithms to study. The context for the maze problems that we're going to do makes this breadth first search a little bit easier, a little bit less abstract. But if you've never seen this algorithm before, it's not a bad idea to do a little bit of reading and walk through that. I'll show you to some resources that you might turn to in order to get hip to what the general idea of that is. But also show you in this video some bad ASCII renderings of how the breadth first search actually works. Similar to labs, the project will involve you downloading some code, running some test cases, and completing some work there. The code that you download is linked up at the top in this p1code.zip, the code pack here. And the contents thereabouts of what are in that are listed in the manifest here. There are a couple files that you'll need to create, notably the main implementation files. They're not provided, rather, this will be your chance to actually create a C file from scratch. We'll take you through some steps in this video of how to set those up so that you can quickly get online and start running test cases to evaluate your progress. But it's also worth looking at some of the other files that are around, and we'll do so during the overview video here. Like with labs, there is a provided makefile, and so it's good to acquaint yourself with the capabilities that are provided in that venerable build system. Like in lab, you'll be able to type things like make help to figure out what's up, but mainly type some make test invocations to run the automated tests that are provided. The project, as you can see on the left-hand side here, it's divided into 4 problems, and they generally progress linearly, with the stuff built in problem 1 maybe being used in problem 2, but certainly later in problem 3, and problem 2 to problem 3 and problem 4. So you generally want to do those in order. And to facilitate individual testing on those problems, the make files provided for the project have a little make test prob1 invocation, make test prob2, and as well, if you wanted to run an individual test, like the 5th test in project 5, or on problem 2 rather, then you type make test and then add this little test num equal 5 business over there. That one's really good to know about, and we'll probably return to it several times as I do demonstrations here, as getting immediate feedback on an individual test that you're trying to pass, rather than waiting for all of the preceding tests to finish, and also seeing the immediate feedback on the terminal rather than having to open up a file for it. That's a handy way as you're grinding away at individual test cases. Okay, let's get oriented in terms of what the project ag looks like. The central sort of mechanism at stake in the project is to read in little data files that have mazes in them. And this is an old school rendering of mazes, just in ASCII characters. The little hashes here, or pounds if you're in Britain, those represent walls that cannot be traversed. Versus the little spaces here, those represent spaces that a player or a mouse or whatever sort of entity is traversing the base can travel through. There's a starting position here, labeled with an S, and an ending position. And generally, these individual positions, I'll refer to them as tiles. They have a row column coordinate. The particular maze that we're looking at here is 7 rows deep, so 1, 2, 3, 4, 5, 6, 7, and 16 columns wide. It's probably too many for me to count, but you can take my word for it. You'll notice here there's a little terminal prompt, and I used the command cat to cat out that maze file. It's called under the data directory. That's mentioned up here in the manifest. Here, there's a bunch of these that are mentioned, and they're used during testing, so I'll try not to lose track of them. But the cat command is used to print those to the terminal screen, and the contents of the file start with a number of rows and columns that are in the maze, so 7 rows deep and 16 wide. The word tiles with a colon, and then each character on here represents the type of tile that is to appear oriented in rows there. You'll eventually, in the last problem, have to write some code that parses this file. So reads in this exact format in order to create a maze. But all of the tests that proceed up to that will evaluate your function's performance on mazes that are created during the tests rather than external files. Of course, in order to run the program independently, you'll need that facility. So you write the function there, and then eventually a maze function, or I say maze solving main that will use the functions you write in the preceding problems in order to construct the following. Read that text in and indicate, oh, here's what I read. Here's where the start tile is at 1, 1. So numbering from 0 row and 0th column there, it's at position 1, 1. And the end tile is here. And a solution to this maze is to start going south, then to the east, and then north, followed by a couple steps to the west there. And this little drawing here is produced as the last step in the program once paths to all the other available positions in the maze have been determined. You can see as well then there's some printing of these are the exact steps to go south, 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 east, 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 north, 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 and west, west in order to go from start to end over here. So this is the overall goal, is to solve a little maze like this. And of course, there'll be a lot of steps in between on that, and we'll take you through a few parts of it. But there's a considerable amount of documentation in the project spec that you would want to consider. Of first and foremost importance is to get an idea of the central algorithm, the breadth first search. There's pseudocode for this written in a Python-esque parlance. It's not a terribly complicated algorithm as they go, but even this thing, as you would want to implement it in C code, is a little bit much, and so is divided into several different functions that carry out various of the effects that are needed here. There's a queue involved, and so the first problem is going to have you create a queue that can store row and column coordinates. There's dealing with the maze and tiles, and so there's some functions that deal with that, and printing and so forth. That'll produce output that looks sort of like this. And then there's the breadth first search functions themselves that will manipulate the data of the queue and the maze and tiles in order to accomplish this. Generally, the idea is that when you would start a breadth first search, you'll take the starting tile position and plop that down into a queue. And then as long as that queue is non-empty, fish off the first elements, explore the neighbors to that, and if you discover any new tiles that are available, plop those down at the end of the queue. And queues being this classic data structure in computer science, things are always at the end. It's a first in, first out affair, as it were. To get a more concrete idea of that, the next session of the project specification walks through a specific example of a maze that's in your code pack, this maze small 3-path maze, where the starting point is actually in the middle. So you can see that as 2, 4. And any point is over here. It's just the short path that might get you there is blocked by some walls. So you're going to have to end up going around. The steps that are shown here then illustrate and are actually outputs if you enable logging for a program, to show what the specific output looks like as the algorithm progresses. So for instance, the first step will be to initialize some data that's needed for the breadth first search. Initially, the maze has this queue and its null has been allocated. So after you do so, the setup should look like there's this initial starting tile that is in the queue. That's the only one. And this 0 here represents the fact that the starting tile is 0, a path length of 0 away from itself. As you would trace the pseudocode over here, you'd find that the first major step then in the breadth first search is to analyze and process the head of that queue, which is 2, 4. There's some log messages printed over here, and this output is controllable by some command line options that you can dictate, hey, please show some level of logging here that shows some amount of detail. Without that option to main, you can see up top, it just prints out what was read in and what the ending solution to the maze was. But if the logging is enabled at different levels, then you see some information that professes what is happening at each stage. So that log message says we'll peel off the first elements, that 2, 4 position, and visit each of its neighbors in the prescribed order, north, south, west, east. On going upwards, there's an open tile there. So this path that was empty has the direction that was searched north copied into it. So the way to reach this tile that's above is just by going 1 step north. Likewise for the 1 step south. The west tile that's here is not reachable because it's a wall, and the east tile is reachable as reported over here, so go east there. This and then having discovered some tiles that have not been visited before, those are all NQ'd. And NQ'd, you can see here 1, 4, that's the north tile from the start position, the south tile, and the east tile. Those are all queued up and ready to be explored. The next BFS step would go forwards and say at the front of the queue here, at the end of this, is tile 1, 4. That was the one that was north of it. And so each of its neighbors, the north, south, west, and east neighbors will be visited. You can see that the north is blocked, as is the east neighbor. The left or west neighbor, that's actually available. And so to get to this tile, there was a north step. And so that's copied over and appended to it is the next step west. So this tile will store, and we'll see sort of examples of this, that's the path to reach it from the starting point is north and then west to go over here. Finally, the south neighbor that's visited here has already been found, and so it's also ignored. And you can see some log messages here indicating that the starting tile that was below it, that's south of it, is skipped because it's not needed. Any of the new tiles, for instance, this one here at position 1, that's row 1, column 3, I think, that is added into the queue. And you can see at the second position here that 1, 3 is now queued up and will be explored later. It's further down in the queue than the preceding elements because it's further away. Now, each of these are only one step away from where the starting point is, whereas 1, 3 is 2 steps away. That's the little 2 that's drawn here, and so forth. So you'll get a sense then that the things that are happening here are all things that you'll eventually implement. And it's a good idea to refer back to these pictures at some point as you would need clarification on what the next steps are. The algorithm proceeds then, picking up the front down of the queue each time and tacking on the new tiles that are found to explore, and anything that's adjacent to them that's available goes into the search queue as well. And you can see that the tiles that appear first in this, they are closer, and as you get further away, those paths are farther. And so when this end tile is discovered, it'll be, by guarantee of the algorithm, the shortest path that can be derived, with ties broken by this ordering of north, south, west, east as the direction of order there. We'll implement a variant of this breadth first search wherein you visit all the tiles. So you completely fill in this maze in this stateful representation here with what's the search length path, what is the search path to get to those things, and this long example that is just a raw program output over there ends with all tiles filled in and the queue being empty, so there's nothing further to explore. That should trigger the breadth first search algorithm to end, and the ending tile, its position is known, so you pick that up and figure out the path was let's see, south, south, east, 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 and north. So south, south, east, 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 north. And that's printed out as the sort of final part to this with these log messages explaining to some extent what that process looks like. So this is the overall idea of the program, and one that you'll complete by working through each of the problems that are listed over here. So the next step along these lines, well, if you wanted more information about what constitutes a breadth first search, there's a nice Wikipedia article on it, and also a good video, I think, that has good visuals and ties specifically to the a discussion of breadth first search in a grid like this, where you don't have to worry about arbitrary neighbors. Instead, it's just sort of north, south, east, west kinds of stuff. So that one's, I think, like 15 minutes long and not a bad watch. Breadth first search is a little bit more general this, and it is stated usually in terms of graphs, as in it's a search over a graph in order to locate from a starting vertex, a starting node, all of the other positions that you can get to in the graph. And so it's not necessarily the case that its breadth first search is restricted to north, south, east, west stuff. If you have more connectivity than that, it's possible to handle. But this makes it easy to visually represent and is a classic sort of beginner computer science problem to solve. Okay, oh, I should mention as well that unlike its close kin depth first search, breadth first search does not involve any recursion. And so this is a purely iterative algorithm. And it's not a bad idea if you want to extend this project to look around at a depth first search incarnation of this to see the recursion that's at stake there, or the use of a stack instead of a queue, and it's interesting, but beyond the scope of what I think I'll talk about going forward. All right, the next step in sort of understanding the nature of the project is to understand what is given. And the design of the project is laid out entirely for you. Your only real need is to implement the required functions. You're free to add some more helper utility functions you want, but in most cases, it won't be necessary. Code what's sort of stated, and you're good to go. To give you a fighting chance at this, there's an outline that's provided in this section, the outline of code for the functions that you need to write, along with some provided data that you'll be required for full credit to use at various points. So this stuff, in a minute, we will copy into a starting file, a C file, and it'll serve as the skeleton for what we'll have to eventually write. Each of the required functions has a bit of documentation associated with it, the intent of the function, any constraints, for instance, that you must allocate using heap memory. I don't know of a good way to do it otherwise in this situation, but it's there, as well as some implementation notes that I provide that are meant to guide you and hint at possible mechanisms that you can exploit to make coding things easier. So you're encouraged to read these, take them to heart, ask questions about them, and so forth. In some cases, the functions also have some example outputs. For instance, here's an example of what the format for printing a queue should look like. And if this doesn't ring a bell, then maybe backtrack a little, because that showed up all over the place when we were walking through the breadth first search states, is that the queue is printed at each step to show that part of the state. As you go down further, you'll see that this is divided into problems. So these queue functions are all associated with problem one. We'll get there in a second. The second problem deals with tiles and mazes. And so there's functions associated with that, examples, outputs, constraints, etc. for these, and so on and so forth as you work down. This is rather long, but a lot of it is documentation. In some cases, the documentation is 2 or 3 times as long as what the actual code looks like. Don't let that fool you into thinking it's easy. Rather, it's just harder to describe what code should do in verbiage rather than just write the concise code itself. If you ever have to write documentation for others from that, you'll probably find that that's the case. The outline here ends with a main function. This is meant to be in a different source file, though. All the remainder of these are in the maze-solve funcs.c file, versus this one is supposed to be in the main maze-solve main.c. And we'll set both of those up shortly. In terms of getting started, these are the steps that we'll do next. We'll copy that into a source file and then set things up so you can actually run the test cases. And your basic cycle to complete this is to read about what the function is supposed to do, write part of it, run some test cases, analyze the results, debug it, consult docs, ask questions, etc., and eventually pass test cases associated with a function, clean up the code so it passes the manual inspection criteria that we'll look at briefly, and then repeat in terms of making progress to the next function. There will be times when you may have to revisit a function because later on, the usage of it causes breakage that wasn't detected in earlier functions. Generally, it's very hard to completely test out a function, and I'm not promising that I've done a great job at that part. Rather, I've provided some test cases for you. You're free to write your own on this stuff, but I haven't had a student yet who has done so. And you're not required to write any tests. Rather, I think the tests that are provided are reasonably comprehensive. Like I said, they aren't guaranteed to make sure that this thing works completely right so that when I use it later, it'll never break. But usually by the end, when you're actually running the full program, if there's some problems, they'll manifest themselves. So if you get stuck for an extended period, like you've been trying to solve a bug for an hour or more, get some help. And you might do so by searching for related examples in lecture and labs and homework. Most of the techniques that you'll need to use in here have already shown up in one of these spots. Particularly labs have shown much of what the C code with linked lists are like. That's very much like the queues. You've been doing some file I/O with treasure maps, so that'll sort of attend to things. You've dealt with some command line arguments on main there, and so those are great sources for it. You can also ask for specific help on Piazza, or visit office hours. If you post, make sure, and you include code, make sure to make that a private post so that no one else steals any of your hard-wrought solution, even though it's buggy. And make sure, as you would post questions about code, that you include, here's what's failing, like the results of the test case. And I'm not sure how to solve this. Here are the things that I've tried. That makes it much easier for staff to answer your questions. So be aware of that. And finally, don't be afraid to take some breaks every now and then. If you're working late in the night, you just cannot get it, go to bed, get some sleep and wake up in the morning refreshed. I cannot tell you how many times I've struggled until 1 a.m. and just called it quits only to have the answers sort of mysteriously appear to me the next morning. It's this wonderful thing. Our brain is capable of running background processes that we're barely aware of. So exploit that. It's only workable if you give yourself enough time to go to bed. If instead the deadline is that night, then you're kind of hosed. So the biggest bit of advice from past students to present students is start this early. That'll give you adequate time to seek help from staff on piazza and office hours, and let your brain do work in the off hours too. Okay, let's get into it a little bit. So the first problem deals with implementing a queue that can hold a row and column position. That should be obviously needed based on the fact that the whole algorithm for breadth first search centers around search this position next, and after you're done with that, search this position next. If you find any new positions, add those in the queue, et cetera, et cetera. And so the first problem deals with implementing this queue. It's just classic dumb data structure based on linked nodes, where there are nodes that store two things, a row column position, and then some function, and then a struct that has a front and rear in a sort of typical linked fashion. And then there are a bunch of functions that manipulate that queue to allocate memory for one, add to the back of it, free it, get it from the front element by setting some integers, and so forth. And so this is a reiteration of what was in the outline earlier, just for the sake of discussion. Beneath it is grading criteria we'll look at right now. But since we're in a position now to actually want to maybe start coding some of this stuff and looking at it, I'll take you through the basic setup part of this. Before that, I'm going to need a couple things. So over here, I've got my editor of choice set up. And this is that 216 sync directory that most of you set up via VS Code. Don't be intimidated by the fact mine looks a little bit different. However you want to get the code, like the starter pack, the code pack on here is fine. My preferred method is to start up a terminal here. And then up at the top here, there's a link to the code pack, similar to what there is in the labs. So I'll just copy that link address and wget the result. It should be there. Let's see. Oops, sorry, I need a space between the URL and the wget there. And so if I refresh my directory, I've got this p1 code zip, and I'll unzip that here, p1 code zip. And there we are. We have the working directory of code in here with the provided stuff that's mentioned. So a couple things to note here. You're free to download that in other or whatever way you want to sync with VS Code. You can put it directly up via wget up onto Grace, or you can get it on your local computer and then upload it via sync on VS Code. Do what you need to get it up there. Hopefully you've practiced that a little bit at this stage through labs and homeworks and such. Another thing to point out is that there is no maze-solve funcs nor maze-solve main.c file in here. We're going to have to create those. So if you get in here and try running some commands, like if I change into the p1 code directory, do like a make test prob1, you'll get immediate errors to say, in order for me to run tests, I need to compile your program. And in order for me to compile your program, I need a source file for that. And so lacking that, there's not much make can do about it. There's nothing to GCC here. That's the first problem that we will sort out here. And we'll do whatever you need to do in order to create a new file. And Emacs, it's my esoteric, like find a new file. And I'll call this maze solve underscore funcs.c. So here's my brand spanking new file with nothing in it, but we'll change that. We'll come back to this little outline of code portion here, highlight just a little bit here, knowing that I can now scroll down. Maybe I'll just use this over here to jump to the next section, and then shift click here, which will carry the selection all the way down to this spot. Do a little control C to copy, jump over here, do a little control V or control Y if you're in Emacs to yank it, and voila, we have our starter code for this thing. We're going to save that initially, but I want to demonstrate we're not quite there yet, because if I do another make test prob1, I'll get a litany of errors saying you had promised that there would be certain functions here. There would be a maze free, a maze something or other. What else is here? RCQ, add rear, RCK, allocated. So the thing that we copied there, there's stubs for functions, but they aren't actually bodies. So this is just a declaration that there shall be such a function. And the header file actually already does that. We can look at that later. At any rate, this does me no good. Rather, instead, I need to give this a body so that the compiler will actually generate something that's executable for a function here. So to do so, and because I don't want to waste too much time on a sensible body yet, I'm just going to return something. This is supposed to return a pointer to an RCQ, and I'll just return null instead. And that should get me a little bit of progress. Now that's one of many functions here. And so I make test prob one again, I'll still get a litany of errors here. But if I go all the way back, you'll see that originally we had one about RCQ alloc. That one's gone now because the function actually exists. Now, if you are sort of the bored type, then you are free to sort of skip the next part here. But I'm going to somewhat tediously go through and fill in definitions for all of these. Void functions don't need to return anything, so I'll literally just plop down an open close paren. And so anything that's marked as return type void, we're good there. This one will be returned in a 0. I don't know if that's right or not, but it's good enough to satisfy the constraint of returning zeros. Let's see, this one's also supposed to return it, so I'll copy paste. Whoops, don't want to eliminate that stuff there. Here, got nothing there. Let's see, this one is void as well. Lots of stuff, a void here. This one's supposed to return a null pointer, so I'll plop that down. So, or sorry, it's supposed to return a pointer, so I'll return null. Over here, another void. Over here, another, let's see, another int. I'll paste that part. Return, let's see, this is a void, so I can get rid of this one. Oh, shoot, well, never mind. Didn't need me to do that. Here, I can just do open closes. Another void function. I didn't realize how many void functions I have in this, but no matter. Put this one below because it's going to be kind of a long line there. And we're getting pretty close here. Return 0. Just open close. Return a 0. And return null. Oh, I think this is the second last function. There's main. Main I don't need to do anything about because it's not supposed to be in this function anyway. Just to make that clear, I'll comment it out. And now if I do a make test prob 1 again, let's see. Some problem at line 414, I hear. That's, let's see, expected identifier before something else. Oh, I probably forgot to eliminate a semicolon or something like that. So let's go back to line 414. And indeed, so take the semicolon off so we don't end the statement. Here's my minimal body to that thing. And if I do a make test prob, look at that. It compiles, it is running the test, it is failing all the tests. But running tests is better than not running tests, even if they all fail. This will allow me to make some incremental progress in terms of passing tests associated with each of these functions. That I think will be the case as well for like problem 2, where all of the necessary functions are now within that stub. For problem 3 as well. Problem 4 actually requires a maze solve main file to be in existence. And so to get that thing up and running, if you want to now, you come back down here and just grab this little main here. I will find and make a new source file, maze solve main.c. Plop down my little ints main here, return 0, and that's all the main I need right now. For posterity, I might want to include the project header. That's up here, mazesolve.h. And so, risk of like forgetting to do so later, I will do so now. And with that in case, quick mention, I won't probably have a chance to do this in many other spots, but when you pound include header files in C, there are 2 syntax options available. One that involves quotes like this, the double quotes, and one that involves angle brackets. So you typically see like stdio.h here. The angle brackets mean the compiler already knows where this header file is. Standard IO is a much used header that's probably in some system directory under on my Linux systems, like /user/include or something like that. But it's a known location where the common system headers are put. This little maze header is something that I wrote. And so the double quotes mean look in a place that is nearby without anything else there, just the double quotes there, it would look in the present directory. You'll also sometimes see like, oh, up one directory is where the header's at, or up one directory and in includes, like that's where it's at. But in our case, the source structure is very simple. It's just like everything's in this one directory. So thus the double quotes are not in a normal system directory, but in the test present directory somewhere nearby on and that's not really going to be needed much, but you will see that syntax in several spots, so it's not a bad thing to be aware of. If we had time at the end of the class to talk more about linking and the compilation process, we might sort of come back to this, but rarely has it been the case that we have such time. So good to know anyway. Okay, with that there, let me return back over to my shell. And if I do the make test prob 4 now, we're good to go because it needed that maze solve main. It was available and combined it with the other source that I wrote and can run all the tests now. So I'm in a position now to make tests, like run all tests, fail all tests, but at least set up so that as you start writing code, you can make some progress on this. Let's do that just to get our feet wet just a little bit. Let me come back over to the funcs and work on sort of the first problem. Before I do this first function over here, this RCQ allocate, as it were, you might want to read through some of the documentation associated with it. I'm going to zip back over to the project spec as it's replicated there as well, and just talk through the essence of what's at stake here. So this will be a standard queue that is housed in a struct, but then the main fields of that struct are pointers to the front and the rear of the queue. And so those will be pointers to nodes. An initially empty queue has a count of 0 and no pointers for front and rear. And the basic premise of this first function is to allocate on the heap one of these empty queues and return a pointer to it. So this is similar in some ways to the other kinds of allocations we've done, allocating a treasure map and so forth. The requirement is heap allocation. So that's definitely going to mean mallocing some stuff. And it's a good sort of idea to sort of think through, okay, how much space would I need for one of these things? What kind of thing is it? And the basic incantation, whatever you malloc, is something like RCQ T star. Let's say I'll just call it Q equals, and then I'll malloc. And then I'll need to figure out how much space to malloc. I could pick a number like 16 or 32, but what I really want is, hey, compiler, figure out how big this struct is. I'm going to have a pointer of one of these, so I'll take the size of Q here. Not sorry, RCQT, the type of that thing. So let's figure out how big that struct is and then return it. For posterity, I might also just feeling like this is the thing that I'm eventually going to return. Now, this part is not quite right yet. And so if I come back over here and run the tests for prob 1, you'll see the first test is of RC allocate free. There's a hint there that, oh, several of the functions are going to be run there. And I'm still failing it, but it's not a bad idea to look at like what's the reasons for the failure now. So a couple things on that. I could look in this source file, this test results prob101 result.md. I can also rerun just this individual test, test num equals 1, with the invocation mess test prob, but restrict yourself to number 1. And this will immediately print out the failure messages in the terminal, which is sometimes convenient. I actually like looking at the source file because it's in Markdown format, and my editor, superior as it is, formats and syntax highlights some of that stuff nicely and allows me to move between sections pretty easily. Up at the top of these results files is a mention of why the test failed. So there were Valgrind errors, so we'll want to look at the section that reports memories out of that. And there was also a mention that it had an exit code of 13. That's usually associated with Valgrind, and so there's probably the same error there. Other than that, though, it looks like, oh, I got the right output here, that this test was allocating something and then printing out what's the count, what's the front, and what's the rear in that. So that's pretty good. Output matches. I expected there to be an output difference here, but hey, we got kind of lucky on this part. Come to think of it, I didn't actually do anything with that count and front and rear stuff, but that might sort of come back to us. If we look back down here, you'll see some complaints that Valgrind has on this stuff. In fact, it's mentioning, hey, there's some stuff here that was uninitialized, something that had size 8 that was initialized. The complaint is coming from the testing program, this maze test maze solve funcs.c at line 105. And if we really want to, we could look at that part there. It's never a bad idea. But there's also a mention from Valgrind, because it's a really nice guy, that the uninitialized stuff was coming from heap allocation that's actually from my stuff here. So over here, the maze solve funcs line 65, that was in their RCQ allocate function. We may as well sort of pull that part up and verify. So that's over here, maze solve funcs.c. Look, line 65, that's where I malloc this block. Now you can see in the test up here, but what it's doing is, after getting this thing back from my function, it prints out what's the count, what's the front, and what's the rear, and so forth. That means, oh, if you're printing out the count, that was malloced, but the value there was never set. It really is uninitialized. And so printing it here is probably what's causing problems like that. And you can see there are several others here, conditional jumps and so forth, that are a little deeper down on. So let's rectify that. What should an empty queue look like? Well, it should have a count of 0. So I'll plop down a count equals 0. And it should also have a front and rear pointer. That's null. So I'll initialize those to be null. Rear equals null. Okay, with that, I am ready to test again. So I'll come back to my shell, recall the history item for this thing, and still getting some problems over here. So let's look around. Output looks good on that. Let's see, 24 bytes. Oh, hang on a second. So this is a different kind of error. 24 bytes in one block are definitely lost. Oh, I've got a memory leak. Okay. So something was malloced but never freed. So there's one allocation here and 0 frees. So something was lost there. The 24 bytes is, I could try to read the T-lays on that. If I jump back over to the header file, you might sort of resolve, like, how big is this thing? Well, it's 8 bytes, or sorry, how big is this thing? It's 2 pointers. That's 16 bytes plus 4 for the count. That's 20. Sometimes the compiler will round that up to 24. So that seems plausible that I didn't deallocate the queue, right? And I'm sort of curious, like, why that would be. Let's look back at the testing results for that. I think you need to reload that thing. So if I look around over here, and you look carefully, okay, allocate the queue, print the stuff out, and RCQ free. Oh, I didn't implement this function yet. In fact, if I remember correctly, over here in the funcs, this one is a little bit lower down and has yet to be implemented. Well, I could try a pot shot here and just say free queue. That's probably not all that needs to happen, because if there are actually any nodes associated with the queue, then that might not work out so well. So we might be revisiting ourselves here. But hey, let's give it a shot and see. And voila, first test passed, great success. The file over here with reports updates to OK, like, and you can see down at the bottom, like, the test is passed. So we're good to go. And you might move on then to test number 2 or something along those lines. And see output for that. Like, doesn't work. This test is going to do things slightly more complex. It's going to actually add something to the queue and free it, which means I'll have to implement the freeing, and also when I free the entire queue, visit all the nodes and get rid of them if there are any there. So there are definitely output differences. There's a segmentation fault here. There's a Valgrind report of things going awry, but you're now in a position to sort of work through some of that on your own and interpret the tea leaves that Valgrind is going to present for that stuff. Okay, I want to return one more time over here to the sort of problem stuff and sort of outline. Once you've worked through most of the problems or the functions that are in here, you may want to look a little bit at the manual inspection criteria. So grading criteria divided into automated tests. That's what happens when you type make test, and you can be certain you're getting 10 points there by passing test cases there. However, there are some things that we will look for that are independent from the tests. This is where if you don't pass all the tests, you can still get partial credit for efforts in completing portions of functions. And we won't deduct credit from your code if it looks like, okay, you didn't pass tests, but it looks like you put forth the effort and satisfied some of the criteria that you hear for this stuff. And so one of the basic overall criteria will be style, and each of the problems has some style points associated with it. Largely, this is dictated by what we've written into our style guide, and it's basic stuff like indent your code in a sane fashion. Pick 2 spaces, pick 4 spaces, but if you have a conditional block or a loop or something like that, please do indent that stuff. And if you're using VS Code, there's even instructions in here to say, here's how you can configure VS Code so anytime you save it automatically indents in a sane fashion for that stuff. Write some comments, use informative variable names, etc., etc. So those things we won't enforce religiously in terms of like commenting, except where it's mentioned in problem criteria, like you must comment some stuff. But if you're utterly bereft of comments in there, expect to lose quite a few style points across this. As well, each of the functions has some things that are looked for in terms of earning more partial credit if you don't quite finish it, and also abiding by certain constraints that are mentioned, like must implement this thing in a certain way, must use a certain technique like this width specifier that printf supports. That's a really handy one to know about, and so it's required that you learn about it in order to use it here. And other things along those lines. So as you finish up your code, it's not a bad idea to review these criteria, make sure that you are abiding by all of them. Or if you get stuck, you might look here for some insight, because sometimes they can hint at ways that you should be doing things there. Each of the problems is divided up in the fashion that we have discussed so far. So the next problem deals with mazes and tiles. The data structures for those are discussed somewhat. There's also a brief discussion of enumerations in C, this way to assign certain numbers named value and get a little bit of type checking so that we're dealing with cardinal directions like north, south, east, west. You could use like 1, 2, 3, 4 for those, but it's a little bit easier on the eyes if you can say north and south and east and west. One of the nice things in C about this is there is maintained this numerical correspondence to those. So you can do things like access within an array, get me the west elements. And since west is the 0, 1, 2, 3th element in here, that'll go into this array and fish out the 3rd element. The directions verbosters, that's a bit of data that you'll use later on. It just has an array with the words, quote, west and quote, south in it that correspond to these indices. Super handy for printing them out, because otherwise these would just print out as numbers. So read some more about enumerations. They're used here, but fairly lightly. And just acknowledge that once those things are set up, you can use what amounts to sort of a global name like West or a global name like Open, and that will be understandable by C because it will correspond it to this value that's in this enumeration over here. Mention that private data, and then so a lot of this is sort of preambles, sort of get oriented, and then the functions themselves and what to write there. We've already got all of this from the outline into our source code, so you can just have at it and start writing functions there. Some of these functions have constraints, and so be cognizant of that part. For instance, I'm trying to find one over here. Oh yeah, the print state, which is this complex function that says, here's an intermediate state during breadth first search, where we've discovered a lot of the tiles and established what their distance is in terms of steps away from the starting tile, which in this instance is up here. What should one do about that part? And there are a couple constraints involved here, such as using the enumerations, using some provided data so that you print out for path length of 10, the lowercase letter a, things along those lines. So be cognizant of that part. Basically, to fulfill the functional requirements, you'll probably have to do something like this. And the constraints are meant to guide you towards the path of least resistance. I have a sort of minor beef to pick with like these wide conditionals where you have 30 different cases of stuff in an if-else or, God forbid, a switch statement. But there are oftentimes much nicer ways to represent that stuff, and those are demonstrated here, where you have a bunch of choices, but those choices correspond to something like a number 1, number 2, number 3, number 4, and the thing that you're looking to do in that case is to fish out a data element to print. And so the provided arrays that show up here in the code outline up at the top, here, those are meant to help with that, to say like, oh, there's certain tile types, like so I can go into this array and fish out those characters. There are certain strings that I might want to print when printing directions. They correspond to the enumeration elements over here. When I am trying to figure out how to change my current coordinates, 5, 2, to go south, then this set of array elements is useful, because if I'm going south, that'll be a row increase of 1, that's down, so to 6, and a column increase of nothing, so 6, 2, but is out. So enumerations are a really great way to give indexing like that, and then data arrays that contain certain elements like this are useful. There are various constraints throughout there on that stuff to use these provided data in a fashion that will make your code a lot cleaner, a lot more generalized. So after dealing with the tiles and mazes, the third section is the breadth first search stuff. Not a bad idea to review the pseudocode, but then parts of that breadth first search are divided into the functions that you're required to write here. For instance, there's a function to process one neighbor, to say from this current row position 5, column position 2, go south. Look at the tile that is there. If it's in bounds, then process it. If it's a wall, ignore it. If it's already been found, ignore it. If it's out of bounds, ignore it, etc. The point of this is to process just a single neighbor that's in a particular direction from some initiating tile. And then as you'd want to process all of the neighbors of a particular tile, there's a step function and an iteration function to repeatedly peel off the first element of the queue and work on that thing to add its neighbors there. The final function in this section is to set the solution. So you go from this kind of thing to walking the path that's south, 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 east, 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 west a couple times that. And so that's where you fill in these little dots over here for this. Grading criteria for that. And then finally, probably the most complex function, the data file processing one, to read from a file a maze and read that into this in-memory data structure, the maze struct there. There you'll have to do a bit with allocating memory for the maze, that's attended to earlier, but then reading each of these characters into an appropriate tile position. Finally, you'll end with main and have to do a little bit of command line processing. So one of the invocations of main is just pass in the maze file. That's shown here. This is form 1. But the second form that we'd seen earlier is to enable logging. So turn on some amount of printing of log messages. That's this additional internal option here, -log of 1. So that sets it to a relatively low option to say what's the order that tiles are visited in. If we set that higher, you'd start to see what's happening at each tile and maybe renditions of what the state looks like there. So there's discussion of logging in one of the earlier sections on the breadth first search. There's a global variable called log level that main will set or is set during testing. And this dictates in this function, some things should be printed if the log level is high enough to show what the progress is like for that. You can see over here that, let's see, in most of these, they have a logging section to say if the log level is of a certain level or higher, then print out messages that look like this logging thing here, where you see log in this message and then this output over here to show what's happened in terms of what the initialization function did, or what's happened in terms of from here to down here, what's changed. This is what the state looks like after that. So I'll digress at this point. My overview videos seem to go on and on and on and so forth, but I think it's a fine time to wrap up. If there is enough time for me, I might try to concoct a makeup credit problem. We'll add some sections for that where you can earn some additional credits that would make up for any mistakes you make on this project or any other projects. But I'll have more explanation of that later if we have time for it. And there's likely to be some makeup problems on later projects as well. As you finish up, it's the same as it is with the labs. So type make zip, get a P1 complete, and then upload that to Gradescope using instructions that I need to upload the pictures for. But sorry for that. But same basic, just plop it down and make sure the automated tests on Gradescope actually run and assign credit for you. That is all I have for. Oh, okay. Before I go, one more thing. Folks always ask, what's the late policy? It's in the syllabus. You can submit up to 2 days late. However, each day late that you submit will cost you an engagement point. You've earned engagement points by completing labs. Some of you are earning additional bonus engagement points by answering piazza questions or coming to lecture and participating there. But generally, no one likes to lose those because they will be bonus credit at the end of the semester if you can get extras. But if you're so unengaged as to need extra time to finish up the project, then that's the cost of that stuff. So make sure you're cognizant of that. Start early, and you're much less likely to have any problems along those lines. All right, I'll fix these pictures. Other than that, we should be good to go. Happy hacking off, and happy snow day for that matter. Cheers.